Hi guys, welcome to our channel. This is our weekly paper reading session. But this time, instead of sharing the works of other people, I'm gonna present my own work with my colleagues. And if you like our channel or like our video, please subscribe or share that with your friends. Okay, the topic is one edit distance FSA and its usage in mispronunciation detection and accent ASR. Today I won't be able to do the first half, but I think I will do the second part next time. You can see it's targeting the mispronunciation detection issue. One example could be a person is saying the word wrong, the decade as, sorry, is saying the word decade as decade. Okay, I guess I spoke too many example of this one. I forgot the correct pronunciation of the word decade. How do you detect and update your pronunciation dictionary affect your acoustic modeling? Because suppose you're using a hybrid or modular ASR system, all the acoustic model of phonetic dictionary and the language model has to be correct. So in order to recognize stuff correctly, well, fail to update this mispronunciation into the dictionary, then you won't be able to recognize the mispronunciations, right? The decade, I think, it will most likely to be recognized as a word D-C-A-Y-E-D. Yeah, suppose the language model is very weak. How do we find this mispronunciation? Can that be used to improve our WER? So with that question, but we analyzed this issue, we found that we have two main challenges. The first is to recognize the native speech in terms of phone recognition. It's very error prone. Take the timid corpus, for example. It's a standard American English corpus. It does have accent, for instance, it will have speech from Midwest and Boston and the west part of the US. And it has an error rate about 15% with a strong phonetic language model. But you can imagine that suppose you run this type of same phonetic decoder on the native speech, I mean, people from all over the world trying to learn English, the error rate could be higher. And it's very hard to find human being and qualified human being to label these mispronunciations. And lots of time they do not agree with each other either. And this is the reason why people would build phone-based finite state acceptor to recognize mispronunciations. Here we use acceptors other than transducers is because this is not a speech recognition. This is more like a phone alignment. You have the ground truth. You have something to start with. For instance, it's the orthodox pronunciation of each word. So all you have to do is to find which phone in the phone sequence of that word is being pronounced wrongly. Is there an insertion, deletion, or substitution error? Right? You don't have to start from the scratch. But people do like to start from scratch. For instance, they build a phoneme decoder, or they don't have to. So they work using the ERN, but this is our work, OEDN. So for the ERN, I think it's the most commonly used approach. It was developed more than 10 years ago, and people are still using that in the speech assessment or mispronunciation detection. Linguisticians will write phone confusion rules. For example, I have a word north, and people may read the different phoneme wrongly. And instead of just having a linear acceptor which goes from 1 to 2 and 2 to 3 and 3 to 5, while in the linear acceptor, between each two nodes, there will be only just one arc, okay? And then this is a setting of the most speech acoustic model training, okay? But if you want to detect the mispronunciations, you just add the confusion rules to these arcs. For instance, suppose n can be L, mispronounced as L. You add another arc here, and you add arc of OW and OAA, right? So after you finish this, you convert or upgrade the linear FSA into a graph, graph of FSA. And then you just send the mispronounced audio into this graph. And once the FSA accepts it, then the most likely path would be obvious to you. Then that path is the mispronounced phone sequence, okay? And this is a phone decoder, right? It's very simple. You just keep looping to the same node 0, right? And accept everything. But the phone array, you can imagine this is going to be very high. But you can say that, oh wait, I can use a phonetic language model. With that being said, you have to have the linguistics again to label the phone sequence, right? And then remember that you don't have to start from scratch. You have the orthodox pronunciation. You're not doing the decoding. You're doing the alignment, you know. So we asked these two questions, okay? How to be independent from linguists, and how do we learn these rules automatically from the data? Because we have the word level pronunciation and the orthodox pronunciation dictionary. Propose our method. This is a general flowchart of how do we train our system. As you can see that we use GMM, but it definitely can be replaced with DN or any advanced acoustic model. First, we start with to train a native model. So I would, in the following video, I would use L1 to represent native, because it's called learner 1 or mother tongue. I would use L2 to refer to the non-native model or GMM. So you can see everything is fairly standard, except that we have this GOP-based GMM alignment, and I will cover this part in the following slides. So how does it work, or how do we make the GOP-based alignment? For those of you who are not familiar with GOP, it's called goodness of pronunciation. You can imagine this is a posterior of the phone after finish the alignment. Okay, you finish the false alignment. Okay, suppose you do the phone alignment, you get where the phone start and end in the utterance, and then you could get a score. I mean, it's the score I meant is the likelihood of the phone. It's a conditional probability, right? Or it's a score in the discriminative model. But we further normalize it. Normalize the score or the likelihood, so we get posterior. So that posterior can be called the GOP score, okay, or GOP value. And once you have these values, you can definitely see that because they are all from 0 to 1, you can find the smallest value of phones in this utterance. That's called most wrongly or most likely mispronounced phone. Okay, suppose it's Y. Then we look at the YI's neighbors, just the left and right neighbors. And then we build a phone acceptor just for this segment. Okay. And you can see that we're not doing this on the whole utterance, which may have dozens of phones. Okay, we only focus on just 3 phones. And that could be very short. It's less than 1 second most of the time. So in this way, we limited the search space to reduce the confusion abilities. And this is how we compose our one edit distance FSA. So you can see that suppose we allow substitution errors for just 1 phone. Okay, you can go from 0 to 1. This is y sub I minus 1, and I 1 to 5. You can have all the possible phones here, and it's called substitution error, right? And then you go from 5 to 3, so it can accept y sub I plus 1. Okay. Same thing for deletion, right? You cannot see here. Sorry about this. It's y I minus 1 to here, then 1 to 3. This will be yi plus 1. The insertion is slightly sophisticated. Take the left phone insertion, for example. You can have 0 to 1, then have all the possibility added here to node 4. Then node 4 to 5 is yi. It does not change, right? Then 5 to 3, you can insert one left phone here. And because we're using word position dependent phones, and that means the L in the word like is a word beginning phone, and the L feel, the L in the word feel is a word ending position. So we take that all into consideration. So you actually do not need that many possibilities because those constraints. And also we have we actually use synonyms. Synonym means that it derives from triphone. Triphone means that we look at the left and right context. So this would further limit the amount of the, what do you call that? The arcs in the FSA, okay. So you can see the features of our FSA. First of all, it does not have the loopback arc as a phone decoder. And we also take the speech segment other than utterance as input. And the third thing is that we call this in multiple rounds, because what does that mean? After we find the most mispronounced phone in the updated phone sequence, right? This one, right? Maybe we'll add something, insert something. Then we call it repeat the procedure. Repeat. We keep iteratively doing this. So that means after we add, suppose we insert the phone here or replace the phone here, we run we updated the scores, and we find that which phone has the lowest GOP score now. Then we work on that phone and its neighbors. We find a new substitutions, insertion, deletion errors. We keep doing this until that all the phones look good to me. So the final phone sequence or the phone alignments are being used in the acoustic model training. Okay. Another thing I want to mention that is why we don't use the 2 edit distance. A lot more transitions from nodes. I think it's possible to have that one, but I want to say that I want to see. First of all, I want to reduce the search space, because if you look at a phone decoder, the search space is enormous. But this one you can maximally reduce the phone search space, and you can always find new mispronounced phones by iteratively using these 1ED or OED FSA. Okay. But I definitely encourage you to explore more sophisticated FSA for accepting the wrongly pronounced words or speech. Let me see if we can explain the whole procedure to you. First of all, I come up with the L1 model. Then I use the L1 model in this proposed GOP-based GMM alignment here. After I got the improved alignments, okay. And this is standard. I run the speaker adaptive training. Then I got a L2 model. It's a non-native GMM in my case. Then I run this model again on the original speech. Then I get new alignments. Then I train my final model. So why do I run this procedure twice? You see, when the GMM alignment twice, GOP-based alignment twice. My thought is there is a difference between accent and the mispronunciations. You see, I have accent, but I pronounced most of my words correctly. I never say the word decade as decade. But mispronunciation is that it's saying the word wrongly. So if you're using the LM model to detect those errors, you're very likely to find many errors. But indeed, it's not, right? So you want to use the L2 model to detect those mispronunciation errors. Okay, so you know what the accent is, and you can find the mispronunciations other than classifying the accent as mispronunciations. All right. And for the record, I also want to mention during decoding, I never updated the phonetic. I never updated the pronunciation dictionary. I was still using the standard dictionary because that won't work if I add new mispronounced terms into the dictionary. I will mention that why I didn't do this in the part 2 of this talk. And this is our setting. You can see that this is a Mandarin. Sorry, this is a Chinese English learners. This is our proprietary data set. I don't think you will be able to find this data set. And you can see the loss value of the acoustic model training did drop after I find better phone alignments. And this is the recognition accuracy. You can see it go down by 0.3% after fusion because the new system provides some information which the first system does not have, and it's further improved the system a lot. You see, I only made the phone error rate recognition error rate drop by 0.3%, but let me tell you, because I was very conservative in detecting the mispronunciations, and maybe it was because those the data set in which the Chinese English learners are doing quite well in terms of the mispronunciations. The only less than 4% of the words were being detected as mispronunciations, and that only 4% things after I corrected, I received a 0.3% gain. I think that's probably okay, right? And most of the detected mispronunciations are substitutions. And what is more important thing is that I think in this work, I also showed that the mispronunciations could be context dependent. I think linguisticians would agree with me on this, but most of the time, they can only write something like a biphone rules. Okay, what do I mean by that? They would say, if you pronounce R after L, you may pronounce the R as something like this. You know, this is a biphone constraint. Only has a history of 1, but I definitely can. The work is mainly on a CNON. I use triphone, so my context is my context window length is like 3, other than just the 2. So it's more contextual dependent, and also I use the word dependent, position dependent phone. And here are some examples of the errors I detected. I have to mention that I have not asked the linguist to check the findings of these. But you definitely can read the paper and see whether these things make sense to you. So I think this is the second point I want to make here is that Besides, I just try to optimize the phone alignments and get a better acoustic model to see if I can improve the WER I did. I also want to see if this procedure can have another byproduct. The byproduct is that the phonological confusion rules. It was handcrafted all by linguisticians, right? But this time I have to generate those rules. It's data dependent, and you can see that especially for personalized speech assessment, these rules derived from the specific person of speech would be very useful, because you can see most of the phonological confusion rules written by the linguisticians were mainly generic. It's for example, they say Chinese learners may not be able to distinguish L and R or L and N, but I can do it well, L and R and L and N, right? The things that I do not do well are the vowels. For example, bat and bat. I know I'm not doing well, but I think it would be nice to have these type of phonological confusion rules dedicated to a specific English learner. Okay. All right. I'm gonna see if I will end here. I think I will end here. So I think next time I will present the part 2. And thank you for being with us. And please subscribe our channel if you like our recording. Thanks so much.